Thanks. Okay, good. Okay, good. So it's my pleasure to introduce Mohammad Barani. He was born in Iran, and he did his bachelor and master's in physics. I'm not going to try to name your institute, IUT. And then he joined Wei Chao Chu's group at West Virginia University. Professor Chu was a student at CU of Shinlin Li. Shinlin was my student. Wei Chao was his student, and Mohammad her student. So he's my grandson, great grandson. Have I got that right? Yeah. Okay. And so he joined the university in West Virginia in 2014, and has been working since 2016 with Wei Chao. And he's a fifth-year PhD student, and he's a Newkirk Fellow here at HAO, Graduate Fellow. And this is a 3-year type appointment, although he'll probably finish his PhD before the 3 years are up. So it's a pleasure to have him working here with me this summer, and I'll just let your title speak for itself.
Okay. Thank you very much. Thanks, everybody, for coming. It's a pleasure for me to be here in this advanced institute. I have this. Yeah. So I'm going to talk about the estimating azimuthal mode number of ultra-low frequency waves based on using multiple GOES, which is a NOAA satellite observations. We used GOES magnetometer data to do the analysis. But I would go through very basics and definitions and necessity of doing this and the importance of doing this. And then I talk about the challenges of this estimation and how it affects our models and the results that we have, that we can expect in our models. So my contributors, so my supervisor back in West Virginia is Wei Chao Tu, and our host, Mary Hudson, here in HAO, Theodore Saris from Greece, and Kevin Pham, who is also working here, and Rob Redmond from NOAA, who provided us these fast antic magnetometer data from GOES satellites. And please stop me if anything I explained was not clear, or if you have questions or anything, just stop me. Thanks. Okay, let's get started. First of all, I talk about the background and the introduction, and I introduce the mode structure. And then I explain a little bit about the previous work and assumptions that we made. And later on, we would see that some of these assumptions are not valid. We have to just not considering those assumptions. And I would talk about the method we used to resolve this mode structure, and apply this method in some event study. And then I would talk about the summary and conclusion, and after that, I would explain a little bit about what we are currently doing and what we are going to do in HAO as my Newkirk Fellowship. Okay, so first of all, I want to introduce the ultra-low frequency waves. So in a magnetosphere, you have magnetic field, which basically comes from the Earth. You can consider as a dipole. But on top of that, you have many other things: electric field fluctuations, magnetic field fluctuations. And before I explain why some of these fluctuations are important, I need to explain you about the 3 main motions of charged particles. So if you consider a magnetic field line like this, and then you can have at least 3 main motions of charged particles: a gyration around magnetic field, and bounce along magnetic field, and drift across the magnetic field. So let's look at how particles move in this magnetic field. So these are magnetic field lines. And then we want to look at the particles. They are moving around magnetic field line. At the same time, they are bouncing back and forth from north to south. And at the same time, they do their gyration, okay, their drift, sorry. So if you look at the gyration around the magnetic field line, the time scale is very short, milliseconds, so short. It is so short that in many of our models, we just assume the particle just stays at the middle of this circle. It's gyrocenter. But the bounce, so let me run it again. So the bounce happens in 0.1 seconds. So it's 10,000 times faster. 10,000 times smaller. And then the drift happens if you look at, for example, at geosynchronous orbit, 1 MeV particles, it takes 1 to 10 minutes for them to make a complete circle around Earth. If you translate this period into frequency, you get this frequency in millihertz. And then if you look at your chart of waves and try to match this, you see it's in PC5, PC4 of ULF waves, ultra low frequency waves. So you see that if there is any wave that is acting in this region, the wave and the particles that are gyrating can talk to each other, okay, because the frequency range are in the same range, okay. Now, so that's why this band of ULF waves is important for us, because the drift frequency and the frequency of these fluctuations are in the same band. Okay. Now, let me explain what is the mode number. So mode number M is nothing but a discretized circular version of K, wave number. Okay. So in one direction you have K, but if you have a circular version of this, you get M. So, in other words, if you try to see how many maximums would fit when you make a complete circle around Earth, it defines M. For example, in this shape, you have 1 maximum and 1 minimum, M is 1. If you have 2, M is 2, and so on and so forth. Well, okay. And, okay, why M is important? As I said, these waves can talk to the particles due to the resonance condition, so they are important. And also, they are one of the inputs in radial diffusion. So in radial diffusion, you have cross-spectral density of your magnetic field pulsations at the frequencies and harmonics of drift. So again, to get those harmonics, you have to consider M values here. So M is very important again. Now, also, because of this importance, M has a significant role in radial diffusion, and radiation belt particles are affected by this effect. So just assume, for example, as I said, okay, if you consider one of the invariants that is associated with the gyro motion, first adiabatic invariant, you see it's the energy of particles perpendicular to the magnetic field divided by the value of the magnetic field. If you put your particles and transport them inward, because you get closer to the Earth, your magnetic field becomes stronger. When it's stronger, because this M has to be fixed because it's an adiabatic invariant, then the energy of particles has to go up. So this way we energize our particles. So if you diffuse your particles, those that are transporting inward, they get energized because of this effect. So that's the importance of mode number. And what we do here is we look at the magnetic field portion or component of these waves. Because waves can be electric field and can be magnetic field. Our focus in magnetic field, and the main reason is the GOES satellite provided us the magnetic field data, not the electric field, because we used data of 2010 for our case study. Again, if I define the background or ambient magnetic field, we typically assume a dipole plus a term of the correction of this dipole because of the compression to the solar wind. When solar wind comes, the magnetic field in the day side that the compression happens is higher, and inversely in the night side is lower. So we use this model. And again, if you want to define the radial diffusion coefficient of the particles, is the mean square displacement of the L value. L is nothing but the radial distance scaled by Earth's radius. Over a time scale tau, which should be much larger than the particle's drift, because you want to let your particle drift enough to show their transport effects. So that's the mathematical expression. Well, because of these two terms, you can have two contributions in your radial diffusion. One is regular or symmetric. The other one is because of this day-night asymmetry. But typically, when we calculate the diffusion coefficient, this first term is dominant. Typically, this term is 1 order of magnitude or so lower. So we can focus on this thing. Again, you see how m dependent is this function, and Pm is nothing but the power spectrum of compressional B at m times drift frequency. And these are the references in case you want to look closer. So let's talk about the previous works and the assumptions. Typically, previously we considered mostly this effect, and what is important is just the m equals 1. Means big scale, you see one maximum and one minimum, and that's it. But later we'll show that this is not realistic. But you have to consider and assume something to start with, and the easier thing is just m equals 1. People don't get to higher typically because it's not easy, for example. So these simplified assumptions of ULF wave mode structure can lead to significant uncertainties in the estimation of DLL. Why? Because if you look at the DLL values, radial diffusion coefficient values, it is a summation of different terms, and each term depends on each m value. So if you consider just first term, it means that you are just consider the very first term and you just neglect the higher terms. So it's very important to have a realistic physical understanding of your mode values. Okay. So what we previously understood from the mode structure is, for example, they saw that m equals 1 mode is generally related to the solar wind dynamic pressure, because when the solar wind buffers the magnetosphere, it produces the big scale fluctuation. And remember that how we define m. When the fluctuation is in big scale, it produces a longer fluctuation scale that is related to the smaller m values. But when the fluctuation gets high in terms of space, you have more fluctuations many places, then your m number is higher. So in other words, we can characterize the fluctuations in terms of time and in terms of space. Time content of fluctuation, we all know, is just frequency. We say, okay, what's the frequency of my wave? But the spatial fluctuation in inner magnetosphere comes from the value, which is m, mode number. Also, the power at m equals 1 has highest fraction of the total power most of the time. Again, this is one of the assumptions we made. And but we also previously also there are measures that during the auroral electrojet in high auroral electrojet or high AE index, you can have a significant power in the modes higher than 1. And mostly you can see this very clearly during the night side because of the injection. Again, the night side pulsations of PC5 band have higher M numbers, typically with respect to day side. Typically, night side is a signature of higher M values, which means a smaller spatial scale than day side. Well, now let's talk about different methods that typically people use to do this mode number analysis. Before that, let's talk about why it is hard. Why typically we consider just first term. Why it is hard to do this estimation? Well, it's hard in three different areas. If you use in situ measurements, you have to have a number of satellite measurements at the same time in the same azimuthal direction, in the same azimuth to cover that. For example, if you want to resolve up to M max mode number, you have to have 2 times of that is equally spaced azimuthally arranged field measurements. So it's very hard to do. And so the other thing is, if you want to use ground magnetometers to do that, you have amplitude attenuation due to the ionospheric screening. Again, you might not be able to resolve high enough mode numbers or high frequency values. If you want to use MHD models like LFM or other models, we always simplify things and have assumptions. These assumptions can affect the reality of the mode number we resolve. For example, the lack of plasma sphere in some of the models can introduce many uncertainties and many errors in the mode number that you estimate. So there are different approaches. One to do this estimation. One is the cross-phase analysis on pairs of real-time ULF wave measurements. This is the method that we are going to follow, this method. The second method is analyzing the Parkes flux in resonance with the current ULF waves. They look at when the resonance condition happens, and then they calculate the M number, for example. And then they can use also models, for example, ULF field models, and they analyze the spectrum of the fields that comes from the results of the models. But our focus is in using in situ data. Okay, how we do this? Mathematically, if you have waves that behaves like this around Earth at, for example, let's say in our case, which we use GOES in geosynchronous orbit, you can very easily mathematically prove that this M is nothing but the relative phase of this wave at 2 points of measurement divided by the separation, azimuthal separation of the 2 measurements. If you can resolve that, you can calculate the M number. And so the good thing that makes this estimation very easy for us using GOES is the satellites are at the fixed almost R value. They don't change their radial distance because they're sitting at the geosynchronous orbit, and also their relative separation don't change much. So when they move around Earth, they move together. These things make the estimation very easily. Contrary to the more sophisticated and methods that you use, satellites that are continuously changing their R value and the separation. So this is easy to do. Okay, I will explain more about how we get this relative phase. Well, so as I explained, the way we calculate M is nothing but the relative phase of the wave at 2 points divided by the separation of the 2 points, azimuthal separation, delta lambda. However, if there are complete periods of pulsation between these 2 points, then you are not going to resolve that. If the separation of your probes are bigger than enough, you can have multiple complete phase wrapping between these 2 points without noticing that. So this is something that we call it 2-pi ambiguity, and it's very important. I'll show that how it affects our mode number structure. Well, so if you just want to put this ambiguity in a mathematical context, this is the way we do it. So you have a calculated M number, and you hope N is 0, and your calculated M number is nothing but the realistic M number. But you always have this thing, N times 360 degrees divided by the delta lambda degrees. So n can be defined and can be interpreted as the level of ambiguity. If n is 0, means you have no ambiguity. What you calculated, what you reported is the realistic one. But if n is 1, means there was one complete period of the waves between your measurement, but you never noticed this. Okay. Well, what is this delta phi? The method we use, if you look at, if you do cross wavelet transform analysis, and you look at the phase spectrum of your analysis, this phase is nothing but the relative phase at the two position of the probes. For example, if you look at your probe U and V, the phase V minus phase U is nothing but delta phi that shows up in your cross wavelet transform. The reason we use the wavelet instead of, for example, windowed FFT is that typically wavelet does a way better job if your signal is non-stationary, which means if the frequency content of your signal with respect to time changes, then FFT doesn't do as good as wavelet a job. And the other thing is, if you have sudden bursts, sudden changes in your field data, again, wavelet can do a better job. And the main reason is that in your Fourier, you decompose your signal based on the harmonics of sine and cosine that are extended to the infinity. But in your wavelet, you decompose your signal into the sine cosine waves that have an envelope, so they don't extend to the infinity. That's the basic difference. Well, as you can see here, delta phi, the relative phase at two positions of a signal can be positive and negative. Okay, what's the meaning of negative? If you look at the definition of the phase speed, omega over k or omega over m in our case, if m becomes negative, your phase speed changes its sign. Means we can switch the direction of propagation or direction of the phase velocity if we see a change in the mode number values. I will come back to this and explain more about this. So, because the way we define our probes, that V is here and U is here, if you have an eastward propagation around Earth, your M values are positive. If we have westward, your M values is negative. Okay. Now let's talk about, now that I explained which method we use, how we do this. Now let's apply this to some events. I chose this time, 27th to 31st of May 2010 storm, and there are some very good reasons why we chose this storm. The first thing is, if you look at let me explain first what this figure is about. This is a IMF-BZ component of the solar wind, IMF-BZ. These are 1, 2, 3, 4, 5 days of data. This is a solar wind velocity. This is a solar wind dynamic pressure. Panel D is auroral electrojet AE index, and E is the flux of more than 0.6 MeV electrons from GOES 13 satellite measurements. And this is a SIM8. This is almost like a DST. So it's like DST values. So the first reason we chose this is during the first day, you have high dynamic pressure. Next day, you have very low dynamic pressure. And you have an opposite in AE index signature. You see low AE, but very high AE. Why is important? Because as I explained before, dynamic pressure and AE are the factors that have a good correlation with your mode structure. So if we can find an event that one of these drivers are on, big, and the other one is off, this is ideal. So this is the reason why we showed this. Because one day you have high pressure, but no AE. Next day, opposite. It's very good to study. And The second reason you see after this, at this event, you have an enhance in the concurrent MEV electrons flux. So it is important. It has application. It increases the flux, this event. And the other reason is exceptionally the data coverage of that what we had available was 5 GO satellites data during this period time, which is kind of exceptional. Because when you have a more coverage, you can resolve this M number way better. So because of these reasons, we picked this event. All right, so let's look at what the configuration of the satellites. Here you have GOES 12, 13, 15, 14, 11, and because they are geosynchronous, they always look at the same place on the Earth, but they are moving. The way they are moving, I put it like this. So when Earth is rotating, they are rotating at the same rate. If Sun is here, this is day side, night side, and let's consider this as an ambient magnetic field. As I should have explained earlier, we focus on the compressional component of the magnetic field pulsation, which is the component along the ambient magnetic field line. And the reason is, if you look at the use the Faraday law, this B parallel gives you E phi in phi direction, and this E phi gives you a transport of particles radially. Okay, so so B parallel is a component that can be responsible for transport of your particles radially inward or backward. That's the reason we focus on this component. That's it. And so, okay, what?
Just go back and remind people what the separation is.
Yeah. Yes. Thanks for. Yeah. So the separation of the satellites where they are moving together is 15 degrees. In geosynchronous, 15 degrees means an hour almost. So they are 1 hour separated, almost fixed, always looking at the same place on the Earth, and they are moving with the Earth. So 1 hour here, 1 hour here, 1 hour here separation, but this is 2 hours, almost 30 degrees. But as I said, this is exceptional. Typically 2 or at best case 3 satellites are available, but here we had 5. So we took advantage of this availability. So see what, let's focus on these 2, GOES 12 and 13, and see what they see when they scan the area in terms of this component of the magnetic field. What they see, the GOES 13 sees this signal, GOES 12 sees this signal. This signal, if you want to look at the spectrum of this signal, is the panel C. Panel D is nothing but the spectrum of GOES 12 signal. This is a cross-spectral density of the signal. Of the signals means kind of the power content of your mode number that we'll talk about. And this is the cross-phase values. So if you remember, cross-phase values or delta phi divided by the separation gives you the mode number. So this has a mode number information in it that we need to extract. Okay. Again, I also mentioned what was the storm commencement, main phase, early recovery, and the late recovery. Okay, if you translate the cross power density and the cross phase into mode number, and if after you do the math and you should look at the visualization, you can have 2 different assumptions for delta phi. You can always assume a relative phase at 2 points, between 2 points of a signal to be in, say, between 0 to 360, which gives you this scenario. Or you can assume this relative phase to be between minus 180 to 180. So again, because phase in this scenario has a negative values, you can have a negative m values. But the question is, which one is realistic? Can we come up with some understanding of which one we choose, which one is more realistic, which one nature behaves? Well, to do that, we need to look at the behavior of pulsations, their power, for example. If you look at the power of low mode numbers, so this is time, and this is low mode number. Because of this assumption, you have all positive. Here, because of the different assumptions, you have positive values and negative values. If you choose this assumption without any reason during high dynamic pressure time, which is half of this from here to here, you see smaller spatial scale fluctuations with some amount of power. So we don't have a reason for that. When the solar wind comes, it agitates everywhere in the day side. So we expect to see a big scale in space. That means we expect to see very low mode values. So we don't have reason for this thing. But if you choose this scenario, you see powers are in low mode number, but the difference is the sign. Well, okay, now we have to deal with the sign. Okay, we think maybe this is more realistic because of the way the solar wind during the high dynamic pressure time behaves. But what about the sign? Can we come up with a understanding of that? So before I explain the sign, let's look at a line plot of mode numbers of the same thing. Again, the question is which scenario is more realistic? From analyzing the power, we think scenario A might be realistic, but the question is, what about the sign? Before I answer this question, let's look at the line plot at different mode numbers. This figure has a lot of information in it. I try to reveal some of them. If you look at the panel A, the black line is the power that comes from all mode numbers. And also I showed dynamic pressure AE and DST index just to align with this structure so that you can see how power in low versus high mode number behaves. So everything blue is low, everything red is high mode. The way I define high is power at m equals 4, 5, all the way to the 12 in our case, and as high. And every mode from 1, 2, 3, and plus or negative is blue. We define it as a low mode power. So as you see during high dynamic pressure, typically you have a low mode signature. Very small, you see red, but during high AE times, almost red is just all of your power. So it shows that, and it's inconsistent with our previous understanding during high AE because of the injection and because of the night side effects that agitates your magnetic field fluctuation. You can have a smaller spatial scale, which means higher M values, but not during the high dynamic pressure time. But interesting, at some time you see the change in the sign. All of the dashed lines are negative values. For example, this is -1 and this is -2. But all of the solid lines are positive. Interesting, after this moment, you all have positive, but before this moment, you all have negative. So what's going on? To understand this, let's look at the same plot, same figure, but put it in the MLT value, in a polar MLT values. If I do this, then it becomes very clear what's the thing. This is the same as this second panel, but I just put it in the MLT sectors. And then what you see after pre-noon, you almost have a solid lines which represent positive M values, and before that you always have a negative almost. So that shows that it shows that this also gives a good estimation of a flow excitation region and the anti-sunward direction. So just solar wind comes from here, then it splits into afternoon and before noon side, and then it just passed away there. So
the direction of propagation.
yes, and direction of propagation is this way, and the opposite way in dawn and dusk. So provided we considered both signs in our case that we did here, that was the scenario A. If go back, this comes from scenario A, but if we consider scenario B, we never get any negative and then negative values. Good. So, okay, we resolve power. Why power should be in lower mode during dynamic pressure, and what is the direction, and why we could we understood the effect of the sign in M. So we now are confident that scenario A is more realistic. The question now is, but we have more than one pair. Each pair gives you one mode estimation, but we have more than one pair. We have multiple probes. Can we get a consistent behavior like this during high dynamic pressure time? The answer is yes. Again, after this point, always you see positive here, positive, positive, and then before you see negative, negative, negative. Great. So also multiple use of satellite confirms that. What about during high AE times? Well, if you look at the high AE times, you don't see much agreement. That's unfortunate. So this green line is absence of data due to the satellite. Again, the pattern is not consistent among different pairs. Well, during high AE time, but during pressure time, it was okay. Then the question is there anything wrong? Is there anything wrong with data? Is there anything wrong with our method? It took a while for us to understand it, and the reason we came up with, and I show and explain that, is during this time, which is signature of smaller spatial fluctuations, the separation of your probes was not small enough to resolve the spatial fluctuations, and that's the reason. Because let's say something is going on here, but you look at here and there, so you cannot resolve those. And also, that's why you don't see a good agreement among these. Then the question is, well, can we do something to approach a more realistic mode number now that we have this problem? Well, initially, the reason that comes to our mind is, okay, call NOAA, ask them spend thousands or hundreds of thousands of dollars, put the satellites closer for just us so that we can resolve mode number. So it's impossible. Another is, okay, try to figure out another way to do this. And this is what I'm going to explain for you. Well, again, I said because of big spatial separation, something is happening in between that you cannot resolve it. It's nothing but ambiguity, 2π ambiguity. So if you look at the mathematics of the ambiguity, instead of using one pair, if I use two pairs like GOES 1312 as a one pair, and the other pair that has some overlap, which means the other pair also looks at the same physics, and also look at the mode numbers that come from these two pairs, and try to reproduce higher M values because of the ambiguity, which means instead of putting n 0 and get this, put n, for example, 0 and 1. And instead of producing a single m for each pair, produce, for example, 3m values or more than 3m values for each pair, and then cross-compare them to see if you get some agreement or not. This is a pattern that we came up with, using more than one pair, multiple probes that are looking at the same area because they are overlapping at that area, and then do the mode analysis considering higher level of ambiguity. And then cross-compare the M values that you get and see if there are some agreement among these. After you've done this process, if you look at the values, so this is the delta M, which means M from one pair minus M from the other pair, before we use this scheme, before we use this method. So this is the amount of agreement you get. If you get 0, which means green, means you get a perfect agreement among different pairs, no problem. Your mode number is realistic, reliable, it's okay. And again, you see during high dynamic pressure time, even before using this new method, you almost have a very good agreement. Great. But during high AE times, the agreement is awful. But after using our scheme, our method, then this is the agreement we get. after cross-comparing, trying to produce higher mode numbers, making sure that which one is realistic, and then choose which the M that you decide to be a realistic one. So this is the agreement which is very promising that we get using more than one pair. Now, two overlapping pair of 1312 and 1512. Okay, another reason that shows that this method works is just looking at the histogram of mode number. If you look at every time frequency being of your signal spectrum, calculate the M number at that beings, and count them, put them in the histogram representation, what you get by just using one pair of 1312 is this behavior. At M equals 12, nothing happens, absence of mode number. But after our scheme, you can, using two multiple overlapping pairs, you get this smooth pattern that also allows higher mode values. And then we expect this.
Yeah, so 12 is based on the limitation of the separation of the spacecraft.
Exactly. Yeah, because you do 2 pi 360 divided by the separation, which is 15, you get 24 total, but minus 12 to 12. Because we, as I explained, we chose the both sign scenario.
So, like when you showed the initial separation between the satellites, that they were all, apart from the one in black.
This one?
Yeah, these other four were all 15 degrees. They were all like very close.
Yeah, these two are 15.
So I feel like
these two are 15.
Does that actually help you with resolving ambiguity so much? I feel like you're just going to have the same ambiguity again if they're all exactly the same distance apart.
So this is, first of all, they are not exactly, but as I showed. So what I showed was this pair and this pair, not the overlapping one, here. And then there is no hope you don't get a good agreement. Again, because something is happening in between, but they cannot resolve that. But now that you are using overlapping pairs and try to, because of the ambiguity equation, you can try to mimic what is the realistic, and does the other pair, which is looking at the same physics, does the other pair confirm that, then you can get a better agreement among of this mode estimation.
Let me just interject that, you might think that you could only resolve this problem by having the spacecraft closer together. But it turns out that by having, another pair further apart, you're able to resolve it.
Yeah. So yes, because of the separation limitation, we couldn't resolve all up more than 12. But because of this method, we could resolve up to 24, which is kind of promising. Good. So in summary and conclusion, we showed that correlation of M structure with dynamic flow pressure, which we showed is signature of low M number, big scale fluctuation is confirmed. During high pressure time, lower modes are dominant. I mean, most of the power comes from this bigger fluctuation scale, spatial scale. Correlation of M structure with AE is also confirmed with respect to previous understanding. During high AE times, we show that higher modes are dominant. Correlation with AE becomes very strong on the night side, as I explained. However, if we compare our results with the MHD models like LFM, we see that AE seems to be more global, not just restricted in the night side than what we typically assume and understood. This is something different. So this model gives a very good estimation of excitation region and the propagation direction of the pulsations. I hope I didn't go too fast, but I have 2 more slides to show you as our current and future work. But if you need more details and discussion, please look at my paper, which is in press in a JGR Space Physics journal. Currently, we have calculated the DLL values based on this believed to be more realistic mode number structure. This is currently doing. And we also need a more sophisticated data to deal with the ambiguity. And we chose MMS to do that because, as you see, MMS probes, the separation of MMS has a 4 tetrahedron shape spacecraft. There are 4 probes. They're so close together that we can resolve what's going on at the position of the probes with a very good certainty. The other, but there are technical difficulties because, as you see, the MMS goes closer and further. So it's not like MMS are not like ghosts that are sitting at the same geosynchronous orbit, and then the spatial also separation is same, constant. It's not the thing. They are always moving closer and expanding and extracting, and they are also sweeping and scanning different radial distances. So it's challenging to do the mode number at any time that these factors are changing. But the advantage of using MMS is they have, because of the separation, which sometimes goes way below this value, degrees, you can get a good mode number understanding, very higher spatial resolution. And also the cadence of data is very good, so the time resolution also is very good, and also the measurements, because they are next generations, their measurements are very accurate. Why MMS is good for M estimation? Because the close separation is ideal, and it gives you very high M values, way higher than this, for example. The variation in L direction gives you an opportunity to study at different L's, but at the same time, the probes themselves are at the same L shell, at the same R. This is good, so we are not worried when you are calculating the M values at the same moment. You are not worried about the too much separation and something comes from one radial distance, something else comes from the other, because they are almost at the same L shell value, L shell. And again, because they are scanning different regions of different radial distances, it's good to see the L dependence of the M values, which is something that in our community we didn't deal with too much. And that's all. Thank you.
Questions? Yes, Joe.
So you've shown molecular jet when it's active, you get these higher modes, so a lot more structure on small scales. And it looked also like there's more westward propagating. I'm not sure if I saw that properly. Say something about what is the physical process that's driving those?
So my focus was more on resolving the M number, but in terms of the drivers, assume that, for example, during substorm, you have ions injecting from some channels in the night side, and they are propagating, and they have their own resonance criteria. And then when they are propagating this, mostly they are propagating this way. But because of the scale, many things at the same time is happening. For example, not just because of this ions injection. You have, for example, Kelvin-Helmholtz instability during the flank region. Because of the shear of the two different flows, this instability can also produce and then propagate fluctuation. And then there are papers that shows that even there are, for example, proposal that shows low mode number can be generated, but when they move around, the power in this low mode number can split into low mode values. Means you have a power, the same mechanism, but during time when it's propagating, the power is split into smaller spatial scales. but I would say it's very hard to confirm which of these drivers are happening and which one is dominant. Sometimes the propagation or direction are opposite. One driver doing something this direction, the other one doing that direction, but which one is dominant, how the mode is behaving when you have a multiple sources. I would say it's very hard to answer the question.
So I'll interject one thing. So because it was your grandfather's PhD. So ions injected from the night side associated with substrate polarization. It's a really cool instability because it's an MHD instability of, so again, these, like this or like this, global oscillations of the Earth's magnetic field, but it's excited by drift bounce resonance of ring current ions with these global MHD oscillations, and that excites a high M number ULF rings, unlike the low M number ones that are being driven, say, by solar wind pressure fluctuations. I mean, it is true that you get Kelvin helmholtz along the flanks that can excite across the range of values, but most of these very high M number ULF rings are excited by substorm injection of ring current ions and this very cool kinetic instability of an MHD mode.
So I could see for low M mode numbers, basically, the system is breathing. It's, you have this pressure, external pressure from the solar wind, and the whole magnetosphere breathes. And the radial dependence more or less in sync. But for high M numbers, I would think that the radial dependence would really confound this analysis. I don't see why high M mode numbers should have a, let's say, an independence of the radial structure. They would have more radial structure than low M numbers. And therefore, how do you know what you're looking at when you're at geosynchronous or, further in and that sort of thing? I'm just wondering how that comes into the analysis.
So you're asking about the driver or the way we can resolve
radial structure, how, when you try to infer the azimuthal mode number, for low M, radial structure is probably not too important. For high M, I'm not sure you can get away with that assumption.
Okay.
But I haven't, you've undoubtedly thought about this a lot more than I. So.
I mean, it may be an analysis of the MMS data where you are looking at radial but it's pretty hard to hear just for the geo.
Illuminate it or confound it.
Yeah.
Okay. Okay.
Just starting to be a comment on the high wave. So I just wonder, when you calculate the wave number, have you considered the coherence between?
Yes.
Yeah, because like you just mentioned, like the ghosts, they have some radial separation. A lot of time, because I study high end,
Yes.
a lot of time the coherence is not good because they're not moving the same wave or wave frequency.
Correct. This is a fantastic question. When you do mode number estimation, regardless of which method you are using, you almost have to do some assumption. For example, as I explained, I just showed that you assume the waves basically behave some kind of harmonically. And from this, you mathematically calculate M, and then you hope that what you see is what you see in the data is what you measure. With respect to the coherence, as you very nicely mentioned, that we always need to make sure that what we measure at the two different points, we are measuring the same thing. Okay. So in this event, the data was very coherent because. So one of the ways you can deal with this is you define a threshold, and you say, okay, I define a threshold under which I don't look at the data. So if you look at these white values are just I just don't look at them because the power was so tiny, was smaller than some threshold that we define, that we are not sure that we are looking at signal versus noise, or noise versus signal, or noise versus noise. One of the ways to do this is just getting rid of after some below some threshold values. But there are fancier methods, spectral methods that gives you even a number that how confident you are that you are looking at data that are coherent. Here I would say is very, very confident, but in some other, if we look at some other events, you must use those spectral analysis to look at the coherence in our data. But here we are confident about the coherence of our data. Yeah.
Maybe sort of a naive question. I know several people already touched about this. You show that, especially during substorms, things are so complicated with high nodes, high M numbers, and also the spatial incoherence at the different locations. So given the limited resource you have, it's more important to resolve exactly the high node or resolve the global distribution of those waves in terms of overall radiation dynamics.
Okay. I would say both, and let's look at. Let me provide some reasoning for that. If you look at radial diffusion coefficients, which M number is one of the inputs, we want to make sure that in higher modes that typically we are not considering. Typically now, if you look at our community, we consider very low mode numbers. We use the power in those mode numbers to calculate our transport and as an input to our transport models. But if, as I showed here, as I explained during high AE times, if you have a significant power in higher mode values, that means that your DLL values without considering those can be different. So then you are inputting some wrong values in your model, so you should not expect to have a realistic values. So
for this diffusion coefficient, you usually just using one number everywhere, or you using, I guess, will be local time dependent, L dependent.
So this is you consider the same L, okay? Because you are assuming that the particles are kind of at the same L shell, and then because of some fluctuation they diffuse, but everything is considered as the same L values. But as they diffuse later time, if you want to consider the diffusion of those particles that are now found in different places, you need to have a DLL values at that L values, which is different than the previous one.
But Don's question, you didn't write down the radial diffusion equation, which is a one-dimensional equation in L, and so it's not assuming any MLT dependence, which of course in the real world there is. And if, for example, you have power over only 180 degrees, you should be reducing your effective diffusion by a half, for example. But that information is not contained in the radial diffusion.
So it's general practice in the radiation.
Well,
yes.
Sky Elkington, for example, is over at last. Will and I think Rachel has done this.
Do you want to use microphone?
Yeah, no, that's okay. No, I don't. That's for you. People will reduce the effectiveness of the radial diffusion by assuming that you only have wave power over a certain longitude range. But the equation itself is just one dimensional. Yeah.
And just to add that, assume that when particles are drifting, half of their time they see some power and next half they don't see. Then any transport phenomenon that you previously considered, now it takes more time for this process to show itself, because now they need more interaction time to see their behavior.
Yes.
This is a silly question.
No.
If you had infinite money and resources, what would a space mission to solve this problem look like?
So, see, why do we resort to models? Because why do we just assume M number? Because we don't have infinite access to everywhere. If I have infinite access to everywhere, just I use a Lorentz force, right? F equals E times Q times electric field plus V cross B. And then I have everything. I just trace my particles through this fields that are everywhere, and then I get the answer. If I have enormous, I would produce a huge amount of satellites that can have a good cover of azimuthally and radially, day side, night side, and then you have a better structure of your waves that you just can use to get the transports of your particles. I would say I built a bunch of satellites.
But I would say that your technique sort of doesn't require as many satellites because you showed in the GOES analysis that you don't have to keep having the satellites closer and closer together. If you have multiple satellites in different pairs, you can go to higher n number without having to have them so closely separated in longitude. That's
the key of our method. So we try to take advantage of multiple pairs while they are looking at the same area when they have overlap. Because we expect to see the same physics when you have an overlap. And then produce higher M's due to the ambiguity and see if you get some agreement or not.
Okay, any more questions? Yes.
One more. Only one more.
So I see that the only consider the compression on the field, right? So how about the Floyd mode? It's also associated with that.
Okay. Yes. So for example, Fahammer 1968 showed that if you have a symmetric background field, like a dipole, what matters is E phi, electric field in the phi direction, and E parallel compressional field. However, like BZ, B parallel or BZ, sorry. But there are papers that later came and showed that if your field map is not symmetric, you can have all of other compressional, toroidal, and poloidal components. But still, because of most of your fields you can consider to be symmetric, and I would say still most of the diffusion coefficient comes from the B parallel and E phi. Just to think of it, assume that you look at the Earth and then E parallel, E in the Z direction is changing. Consider the Faraday's law. dB over dt gives you a curl of E, so E becomes in the phi direction. And now having E with the E in phi and B ambient field, dipole field in Z, E cross B drift gives you particles to transport in radial direction. Depending on which E phi was in eastward and westward, you can get radially outward or inward, respectively.
Yeah, so just to wrap up, anything that gives you an E5, any fuel uprate that has an E5 is going to be more effective on the radial transport. And it's not just the compressional one, but that's the one that he chose to study that has an E5 associated with it.
Yeah, because if you go back to one slide of showing a whole strong effect on the power of the compressional mode distribution, you will see it's more or less focused.
Which one?
This one. Yeah, it's more or less focused on the main phase. Right. By using early recovery or late recovery phase, you see less power in the compression mode. But if you do that of the Floyd mode, you might see more Floyd mode with power in the
Which has an E5 associated with it. That's
Yeah.
Yeah.
So that's one thing that will contribute also to
certainly will. Yeah. Okay,
Thanks.
we better wrap it up.
Thank you. Thanks, everybody.
Yeah, so where we were.
Anyway.
Yeah, so it's like you have.
Thank you.
Have these